Okay, so today we'll be starting the second lecture, and this is about some elementary statistical inferences. So we'll be covering chapter 2 of the textbook. So we are starting chapter 2 and eventually we'll finish it. Okay, so let's get started. So chapter 2 that we are starting today, it's about some elementary statistical inferences. So this is my second lecture. So this is from the textbook, chapter 4, some elementary statistical inferences. Okay, we'll try to understand what it is. And in this section, we'll be using our knowledge from the last class, so meaning that we understood something regarding the student's t distribution. So we understood the chi-square distribution, and here you'll see everything sort of in action. Okay. All right. In a typical statistical problem, so in a real world problem, in a typical real world problem, so we usually have a random variable x is of interest. But the problem is, I mean, it's PDF or probability mass function, PMF, it's not known. Okay, so I mean, we wrote some very nice probability density function or probability mass function, such as for probability mass function, we studied the binomial or say Poisson, or for continuous case, we studied the probability density function. We studied normal distributions. You know the form of that, okay? But and we know everything. We pretend that we know everything and we work with it. But what happens typically is fx, or which is a probability density function, or px, which is a probability mass function, is not known. Now, being unknown, it's of two different kinds. Um, it's not known in two different ways. One is partially unknown, and sometimes it's completely unknown. So this is unknown in a real world problem. When, I mean, of course, for the textbook problems or in class, we consider the problems when it's known, like we know everything. But typically, if you're dealing with a real world problem, so this fx or px is not really known. Now, they're not known in two different ways. One is fx or px are completely unknown. You don't know anything about it. You don't know if it's normal, you don't know if it's binomial or what kind of distribution, we have no idea. Okay. The second one is, I mean, in this case, there are techniques, but the second one is of our interest in this section. The form of fx or px is known. That means, suppose we know that it follows Gaussian distribution or normal distribution. So it's the form is known, so we know what the probability distribution function looks like. Sorry, probability density function looks like. But what we don't know is known with respect to a parameter theta, where theta may be a vector. Okay, I'll give some examples on this one. For example, so this is, let's call this one for 2, 1 and 2. So we deal with 2, not with 1 here. right? So what will be an example? So suppose X is a random variable that is known to follow a normal distribution with mu sigma squared. Okay. So in this case, the form of the PDF is unknown with respect. So the form of the PDF is known. For example, we know what this PDF looks like. So fx here is 1 over sigma square root of 2 pi e to the minus 1 half x minus mu over sigma squared. So for minus infinity less than x less than infinity, right? So that is the form of the PDF. But what is not known is what this sigma is or what this mu is. So in this case, theta, which can be a vector, mu and sigma, is unknown. And that is something left, the job for us is to find it from some sort of data. We'll see this in this entire section. We'll be developing tools to sort of estimate this unknown parameters from the given data. Please note that what is known here is we know at least it satisfies a structure of this form. Okay, what we don't know is what this mu or what this sigma is. Another example. So this is one example. Or it can be, say, suppose another example. So X has the exponential distribution. Okay. So in this case, we can say that fx satisfies the form lambda e to the minus lambda x for x bigger than 0, 0, x less than 0. What is unknown is unknown. We know this form. This form is known of PDF. It is known. What is by form? I mean there is a constant. We know that there is a constant lambda, so that the fx looks like this one. What is unknown is lambda. So in this case, theta is lambda. What is theta? Remember that we say that the probability density function or probability mass function is unknown, is known with respect to a parameter, the theta, and that theta is unknown. Okay? So we need to find this lambda here. So this theta is lambda here. Okay, another example. So all this, I mean, this couple of examples are for the probability density function. So suppose we consider a probability mass function. Suppose X satisfies a binomial distribution with NP. If you recall, what is a binomial distribution? So it's P of, again, P of X equals to K would be equals to N choose K, P to the K, 1 minus P to the N minus K, where this K can be 0, 1, 2, all the way up to N. Right? So it's a probability mass function. So this is the probability mass function because it's a discrete time distribution. We know the form of the distribution is this one, but suppose so N is known, but P is unknown. So we need to estimate theta equals to P. Okay. All right. So these are examples that we typically want to find. So the goal. So the goal is we need to find this unknown value theta from the data set. Okay. Mathematically speaking, I'll write this one time. So the goal is the random variable X has PDF fx or PMF px with some unknown as we have seen theta. So for instance, for the case of the for what I wrote here, for the case of binomial, so we can say that it has a PMF of this one where this P is unknown. So where P is theta, right? Just to emphasize that this F and P are dependent on theta, it's written as, so we write that to show the dependence on theta, we write this F of X semicolon theta or P of X semicolon theta. So basically we write this Fx as this one and Px this one where this theta is unknown. It's nothing more sophisticated than this one. So for instance, we can write in the previous example. So if you see that right here, for the case of exponential distribution, we write this as fx equals to lambda to the minus lambda x. So we write this as if this lambda is unknown, so we write f of x comma lambda. Okay, it's just to emphasize that lambda is unknown. We should need to find out. Okay. Where this theta in some set omega for a specific set omega. It's not also hard to understand because I mean this unknown cannot be just any number. For instance, we know for the last example, if this theta is p, this theta cannot be just any number. Theta got to be between 0 and 1, right? So this omega is this omega is a set which is a set consisting of any number between 0 and 1. Here this theta, which is lambda, so and we know this lambda is always bigger than 0, so this theta is bigger than 0. It cannot be just any number, it's bigger than 0. Okay, so here theta bigger than 0. So in the case of the first example, this is in the case of the second example, this is this one. Okay. Of the distribution. And goal, which I wrote before, is to estimate theta. Okay. So this is the real statistical analysis in the sense that we see a bunch of data, right? In the real life, we see a bunch of data. Our real goal is to find the distribution. And I mean, what we have done in the previous courses or so far, whatever we have done, it's sort of idealistic in the sense that we pretend that we know everything about the distribution, which is in real life not true. So we don't know everything. So especially we have little idea about the parameters. So these parameters are obtained using some sort of techniques, and that is something we are going to study in this section. Okay. Okay, so that is our goal. Now let's see. In order to find this, we will be assuming that suppose that we are seeing some sample. Okay. So the way to write it is the assumption. What do you assume? So so here is the underlying assumption for this thing. The information the sample observations are coming from the same distribution X. And we denote Xn. Okay. Once again, a good example to memorize here is suppose we are we have a class with 100 students, and we have reasons to believe that the student distribution, like the students' heights, they are following a certain distribution, say X. Okay, we don't know this X, but at least whatever student's height we are measuring, so each student, their height will be satisfied. So for the first student, the student's height is x1. For the second student, the student's height is x2. For the nth student, the student's height is xn. Each of these are random variable. So now so everything here is a random variables, and we are assuming that each of these numbers are independent, and each of these are satisfying the same distribution as the original x. Okay, and in this case we called it IIDs. And what are the numbers? So when the samples are actually drawn, that means when we really observe a particular student's height, we use say x1 equals to x1, x2 equals to x2. We found this xn equals to little xn. I'm using the lowercase letters for this xn. Okay. So this quantity, so x1, x2, xn, is called a realization. So our values or realizations of the sample. Okay, so we are drawing. So we are. So when we find the like, suppose we are restricting this out of the 100 student class, and suppose this n is 10. So that suppose we are just taking 10 students at random, and we are trying to observe their heights, right? So what we are doing is basically, so we are listing their heights. So maybe 4 feet 9 inches, 6 feet, 5 foot 5 inches, etc. So this little number, so these are the actual observed values. So every time you do confirm, every time you perform a different operation, these numbers are changed, right? So these are the realizations are changed every time you perform the operation. Okay, so now we're ready to define something which is very important. With this prelude, so here's my definition. So definition. The random variables x1, x2, xn are IID. Remember what is an IID? So each of these are independent, and each of these is following the same distribution. Namely, x1 satisfies the distribution of x, x2 satisfies x, and everything has the same distribution. So that is independent and identical distributed. Okay. The random variables x1, x2, xn are IID. Let's write this. If the random variables, if the random variables x1 all the way up to xn are IID, then these random variables constitute a random sample of size n from a common distribution. What distribution? That is x. All right. So x1, x2, whatever they're following, that is fine. So the common distribution is that. So that is the definition of a random sample. Finally, the final definition. So this is a definition of random sample. I think when we studied the sample mean and sample variance, we also did that. So basically, what is I mean, if we have a n IID, so that's a random sample, right? Final definition is something very important. Let x1, x2, xn denote a sample of size or sample on a random variable x. What does it mean? It means that this x1, x2, xn, this is an IID, and what is the common distribution? That is x. That's it. That's the meaning of the sentence. Let us consider a function t, which is given by t of x1, x2, xn. Now, please note that what it is. An example can be, so here is an example. I'll complete this, but before doing that, example. So suppose I say t equals to say x1 plus x2 all the way up to xn. Suppose t is the addition of the n numbers. Okay. Is this random or is that deterministic? It's random because every time I observe n samples, so x1, x2, xn, x1 is my first sample, x2 is my second sample. So think about the example when we once again considered the heights of the students. So if we have 10 students, and if I add the heights of the 10 students, that's the value of t for that sample. Okay. Now, if I choose a different sample, meaning that suppose we have now 10 other students, then the value of t would be different. But x1 would be my first student, like whoever is the first student. So the height of that person would be x1, and x2 is the second person's height, and so on. So this will be another number, another t. So this will be a different number, right? So every time I run an experiment, this t value will be different. So t is a random variable. So this is an example of t. Okay, it can be say x was for some reason. If you don't want this, I mean, number to be positive, it can be just negative of this whole thing. It can be x1 squared minus x2 squared plus x3 squared minus x4 squared or whatever. Okay, any function t. Okay, so let this be a function of the sample. Okay. Then t is called our statistic. A statistic. Okay. Now, once we run an experiment, when we see it, we can find a value of the t. Just like before, that would be an observation. That would be a realization of t. Okay. Now, with this definition, we are ready to proceed. And we want to find something meaningful. Remember, what is our goal? So goal is the same. So with all this, what we're trying to do, we'll be given with a PDF or PMF, and we'll be trying to estimate the best value of theta. So what would be, for given a data, what should be the value of P? Okay. So how do you find the value of P given a set of data? Now, there are various ways of finding it. The first way is called the point estimation. All right. So what would be doing is the following. So this is usually done with the help of the maximum likelihood estimator. We'll be studying this particular estimator in details later part of this course. So I mean, at this point, we'll not really study it too much, but I have to mention it. So let me just mention it. So so let me show you. So step one is to say that the unknown parameter or unknown vector theta and the PDF is f of x theta. Okay. Think about say a Gaussian distribution where this theta can be a vector mu and theta. So we know the form, but we have no idea about this mu or sigma. Okay. Consider a sample. So consider n sample with realization or we don't need this. Okay. So now if we have n samples, so that means the random variable now is x1, x2, xn, right? That is, and they're IID. They are independent and identically distributed. What kind of distribution each follows? F of x theta. Right? All we don't know theta, but we know the form of this one. So what is the joint distribution? Remember from the previous course that if they're independent, we can simply multiply the individual densities to construct a joint density. So the joint distribution would be f of, say, x1 theta, f of x2 theta, f of xn theta. Okay, so these are the so I'm just using different letters just to signify that they are different distributions. So they are from the different distributions. So here for the first like f of x1 theta is so here the variable is x1 for the PDF. For f of x2 theta, here the variable is x2. For what I mean is, suppose we have two distributions, say x1 satisfies normal distribution with mu sigma squared, x2 satisfies normal distribution with mu sigma squared, and x1 and x2 are independent. Okay, then what is the joint PDF? So the joint PDF would be basically product of these two. So it's 1 over sigma square root of 2 pi e to the minus 1/2 x minus mu over sigma squared. That is for the first one. I can write this as x1 multiplied by the other one, sigma square root of 2 pi e to the minus 1/2 x2 minus mu over sigma squared. That's for the second one, right? So here minus infinity less than x1 less than infinity and minus infinity less than x2 less than infinity. I'm just writing x1 and x2 just to distinguish that they're coming from two different distributions for no other reason. Otherwise, you can simply write it for x1, but then it'll be confusing. It will not be, I mean, it will be x1 minus mu squared over sigma squared and x1 minus mu over sigma squared, and you can sort of combine those together, which is not correct. So since we're writing joint PDF, so we usually wrote it as f x comma y, if you recall the previous course. So this is, sorry, in this case, it will be, according to my notation, it's x1 comma x2, f of x1 comma x2. That's the joint PDF. That is what we are writing. Now, what is this theta business? So here, look at the first quantity. It depends on mu and sigma. So that's my theta for the first function. For the second one, it also depends on mu and sigma. That's my second function, and so on. Okay. Now in mathematics, this kind of expressions are usually combined, written as a product notation. So this is product of f of, we just write this, so x1, x2, and we are taking all the products. So xi semicolon theta, where I runs from 1 to n. Okay. That's how it's written, the joint distribution. Okay. And that's it. So step one, remember, so for step one, we are trying to construct the maximum likelihood estimator. So this is it. This is the maximum likelihood estimator. And we write this as L theta. It's called the max likelihood estimator, or in short, MLE. Okay. So it's written simply as the product of I from 1 to n, f of xi theta. That is the conclusion of my first step. Okay. Okay. Sorry, we didn't compute the maximum likelihood yet. So this is actually the likelihood function. Sorry about that. Yeah, I mean, in step two, I'll be writing the maximum. So it's a likelihood function. This is likelihood function. And that is the goal of step one, to find a likelihood function. Okay. What is the goal? The goal is somehow use this function to find the value of theta that will be used for the as a correct value of theta based on the sample. Okay, so let's do that. That's step two. Step two. An often used estimate is the value of theta that provides the maximum of L theta. It's a problem from calculus. So you have a function L, likelihood function, and you're trying to maximize it. If it is unique, this is called the maximum likelihood estimator. I will do a bunch of examples, so we'll see. It's MLE. And we denote it by theta hat. So theta hat is a value of theta that maximizes this quantity. So this is well, how do you compute it? It's calculus. Again, I'm in step two. So step one is a construction of the likelihood function, and step two is to maximize it. It's another way of, so that is, so theta hat is a value that maximizes this L theta. So we write this as the following mathematically: is the argmax. What is argmax? The value of theta that maximizes L theta. That's it. That's meaning. So theta hat is, mathematically speaking, it's argmax of L theta. How do you compute? In practice, so that I mean, and once you find theta hat, you are done. In practice, usually look at the form of this one. It's a gigantic product. So if it's 100 numbers, if n 100, it's a product of 100. So and we can of course maximize it, but we observe that if we take the logarithm of that, you know that log of A times B times C, it's simply log of A plus log of B plus log of C, right? So it becomes addition, which is easier to handle, little easier to handle compared to multiplication. So later, so what we do is we take the log of this likelihood function, which is the log likelihood function, and we maximize it. It's exactly same as what I just discussed, step 1 and step 2, except just to make it a little easier, we take the logarithm of this of both sides. So in practice, what we do is we consider the log likelihood function. Okay, so, and we denote it by L of theta. This is a lowercase l, okay, which is the log of the uppercase L theta. So this is a log likelihood function. I'm not going anywhere from anywhere. We are not deviating from the step 2. We are just in step 2, but this is how it's done in practice. Okay. Now this is an increasing function. So this is an increasing function. So L theta is an increasing function. Therefore, whatever value of theta maximizes this L theta. So that means whatever value of theta maximizes L theta. That means the quantity that we're looking for, the maximum likelihood estimator, will also maximize L theta. Okay. So as long as you're finding the value maximum of this L theta, that will also maximize this big L of theta. Okay. Now, how do you typically maximize a function? This one, so typically from calculus. So what we do is we compute. So this, if theta is vector, so if theta is a vector, it may be. I mean, it may look like very abstract, but pretty soon we'll do some examples. So please bear with me for 1 second. So, so if theta is vector, so to maximize this L theta, we compute, d of L theta over d theta and equate that to 0. Why this partial notation? This so remember that this theta can be a vector. Oh, I already wrote it. Theta is a vector. So theta has different components. So you differentiate with respect to every component, set that equal to 0. And whatever you solve this equation, and from there you get the estimate. So these are, you get the value of theta. Okay, that's not really the only condition. You need to um, consider the second order conditions to check that these critical points are really maximum. But we'll do it later. But this is the general framework. So what is the general framework? So first step 1, and now I'll be doing some examples. So step 1 is we'll be finding some likelihood function like this one. In step 2, we'll try to maximize that likelihood function in this way. So we'll take the logarithm of that and we'll try to maximize it. Okay, whatever value of theta maximize it, that is a number we are looking for. So let's see some concrete examples so that we can feel better about this one. Okay, so let's see. So here is an example. Suppose, say the exponential distribution. Now, what do I mean by that? So I mean that suppose that we have a sample x1, x2, all the way up to xn. They follow the exponential distribution, say with 1 over theta. What does it mean? So that means individually. So that means individually. So we know the common distribution is fx, which is equals to 1 over theta e to the minus x over theta for x positive and 0 otherwise. We know that this is the structure of the common distribution. What we don't know what this theta is. Okay. So now, step 1. What is the likelihood function? So the likelihood function, L theta, would be the product of I from 1 to n f of xi theta. What is f of xi theta? So this is same as f of x theta. So that means this is f of x1 theta, f of x2 theta, all the way up to f of xn theta, right? So that means I'm trying to multiply all these theta times. So this is really speaking, it's theta is multiplied n times, and then we have e to the, it's a product of, let me just write product notation, I from 1 to n, e of minus xi over theta, right? That's it. I just pulled out 1 over theta in because every term has 1 over theta. So we're multiplying n of those. So it's 1 over theta in, right? Okay, step 1 done. Likelihood function is found. Step 2, let's compute the log likelihood functions. So L theta, which is the log of L theta, right? So this is going to be log of 1 over theta to the n, product of I from 1 to n, e to the minus xi over theta, which is really the first term is log of 1 over theta to the n, so which is minus n log theta. And then we have bunch of terms like this one. And log, by the way, in this entire course, whenever you see log, that is log with respect to e. It's an exponential logarithm, okay? So now these terms are basically so when I take the product, it becomes a summation. So it's a summation I from 1 to n xi over theta, isn't it? So this is basically, let me just massage it a little bit, log of theta minus 1 over theta, I from 1 to n xi. That is the L theta. So what is the unknown? So here the unknown, the only unknown is theta, one-dimensional vector. Okay. So how do you maximize this? So to maximize L theta, we take the we differentiate this L theta with respect to, there is just one variable theta, so I'll differentiate with respect to that. Now let's do that. So if I differentiate that, so if I differentiate log of theta, it's 1 over theta, so it's minus n over theta. Now this 1 over theta, if I differentiate, it's minus 1 over theta squared, right? So it's 1 over theta squared, and this is independent of theta, so it does not change. I from 1 to n xi. Okay. This is the first derivative, and let's compute the second derivative too, because you know that in order to maximize the second derivative, we got to be negative, right? So let's compute the second derivative. So L2, the second derivative would be, let's see. So it's 1 over theta, so it's going to be n over theta squared, right? Minus so the first, so if I differentiate 1 over theta, it's this one, and this is going to be minus 2 over theta squared, I from 1 to n xi. That's my second derivative. Okay. So what do you have to do? If you like, I think it's better if I just break it in 3 steps. So where is my second step? So that was my step 1. Step 1 was to construct this one that we have done. Step 2, I said, which is correct. So step 2 is this one. And let's call this one, when you compute the maximization, as step 3. Okay. So this is my step 3. So step 1 is just L theta. Step 2 is little l of theta. Step 3 is we are maximizing this, which involves some calculus. Okay. All right, so let's see if we can figure it out. So I can always solve this equation to find theta. So now L d theta equals to 0 would give me what? It gives me minus n over theta plus 1 over theta squared I from 1 to n xi equals 0. All right. So if I solve this for, I want to find theta. So if I want to find, so it's n over theta is 1 over theta squared summation I from 1 to n xi. And now if I solve for theta, so theta equals 1 over n I from 1 to n xi. That is the theta we found. Now, what does it tell me about the second derivative? So if I use this for the first derivative, the second derivative becomes, so theta 2 is, it's n over, sorry, this is theta cubed. That was theta cubed, sorry about that, for the last one. So it's really n over theta squared minus 2 over just a second. So this is 2 over theta cubed. So that means 2 over theta is this one. So it's 1 over n I from 1 to n xi cubed. I from 1 to, I think it's a little messy. So let me just do it in a little different way. But since I've already done it, I can change it now. Okay, but anyway. So this is this one, right? We observe that this is going to be n over theta squared minus, there is a n cubed. So it's 2n cubed. And then we have, so this is summation I from 1 to n xi squared, right? And now let's replace the value of theta here. So it's going to be theta squared is n cubed over summation I from 1 to n xi squared minus 2 n cubed summation I from 1 to n xi squared, which is minus n cubed over summation I from 1 to n xi cubed. Sorry, x squared, which is negative. So we are good. So once we're taking the second derivative is always negative. So hence, theta equals what we found right here. Maximizes L theta. And in effect, big L theta. That's it. So we say that, so then the maximum likelihood function, so let me now go back to the previous one. So we say that this theta hat, that is maximizing the whatever is maximizes this L theta. So this is called the maximum likelihood function. We write it in the following way. So we write, so this is step 3. So theta hat is therefore, now it's a function of the random variables. So we try to write this in terms of original random variable. So it's 1 over n I from, so xi is a realization of big Xi, right? So the way we typically write it, we write that this theta hat is this one. Okay. So this is the statistic. So this is the statistics that we developed for this example. All right. So this statistic is the maximum likelihood estimator of theta. Okay. So here is what we have done. So once we found this theta, we go back to the original random variable and we develop the statistic for the maximum likelihood estimator as this one. Okay. So this we go from xi to big Xi and we call this one as a statistic. Remember what is a statistic? So there's a function of random variables. So there are a bunch of random variables x1, x2, xn. So now we are creating this theta hat as a summation of xi over n. And if you recall our discussion in the last class, this is nothing but x bar. That is the sample mean. Okay. So sample mean is a good estimate for this theta for the original distribution. Once again, so see where we started off. So we started off the process by saying that, okay, we know that x1, x2, xn, they follow certain exponential distribution with 1 over theta. We don't know what this theta is, okay? Now, what we found finally is then, okay, so if you give me 10 numbers, and what I'll simply do is I'll simply compute this one, and whatever the value of theta hat is, that I'll use as a sample mean. That's it. So that will be used here. Okay. All right. One little important thing. And this is something we also discussed in the previous class. It's called, now we are formally going to write it, definition. It's regarding the unbiasedness. Okay. Let x1, x2, xn denote a sample on a random variable x with PDF f of x theta for theta in certain domain. Okay. Let t equals t of x1, x2, xn be a statistic. We say t, we say that t is an unbiased estimator of theta, provided E of t is theta. Okay. That's the definition. So if you can construct a statistic, which is a function of all this random variable, and if E of t is theta, that's the quantity we are trying to estimate, then we say that t is an unbiased estimator of theta. Now back to last example. We found we found theta hat equals x bar. Okay, we found this. What is then E of theta hat? Which is E of x bar, right? If you recall my last class, what is E of x bar? So E of x bar, it should be mu, where mu is the population mean. Okay. Again, if you took the the previous course and you forgot, here is a good time to recap. So let me just remind you. So suppose that x here is an aside, but it's sort of relevant to this computation. So suppose X satisfies exponential distribution with 1 over theta. In the last course, or in Stat 311, we proved that in this case, E of X is theta. We proved it. Okay. So in our example, this bunch of x1, x2, xn, so they are drawn from this distribution. So what is the mean? So for x1, x2, xn, 1 over lambda, their expectation are the same. And that is lambda. I think, I'm sorry, so I think we wrote as theta. So let's write theta. Theta. This is my mu. That is for the entire population. So for the so this by population I mean, so every x1, x2, each of these are actually satisfying the distribution of x. So the population mean is mu, and that is theta, right? So this is really theta from here. Okay. So what we found is E of theta hat is theta. What is theta hat? Theta hat is the one that we constructed. So this theta hat is the statistic that we found. And since this is true, we say that this theta hat is an unbiased estimator of theta. Okay. That is the goal, and that is what we found. So we developed a technique of, so there are 3 steps. So first step was, let me just quickly go back. So first step, we are given with a bunch of exponential distributions. We construct this L theta, which is the likelihood function. Then we have the log likelihood function. And then in step 3, maximize it. And after we done the maximization, we found that our correct value of theta that maximizes should be this one. Okay. Now we say that, okay, so we have this little xi. So then if you want to construct a statistic, so statistics should depend on the random variable. So we'll replace this xi's by the big xi's, and we construct a statistic accordingly. And from there, we say that, okay, so now we can recognize this, and this is x bar. So this theta hat is x bar. Okay, so once we have that, and then we observe that E of theta hat, the way we construct it, so this is really same as theta. So, and hence this theta bar is a unbiased estimator of theta. All right, so this is a very good example for understanding the likelihood function. Let me now do a couple of more. Second example. Let's consider the normal distribution, which is so famous, right? So suppose we have X satisfies a normal distribution with mean mu sigma squared. What does it mean? So that means the population mean is mu and population variance is sigma squared. I don't know why the screen is a little hazy. Okay, so suppose we consider that this X satisfies a normal distribution with mean mu and variance sigma squared, right? So there we have a random sample x1, x2, xn, random sample on X. What does it mean? Each of these follow normal distribution mu sigma squared. Okay. So what is the unknown? So unknown is we don't know mu and we don't know sigma squared. So we don't know mu and sigma. That would be my theta. Here theta is a vector. So this theta is a vector. In the last example, it was just a number, but in this case, it's a vector. It's a vector of two elements, mu and sigma. A vector simply means it has more than one components. Okay. Step one. It's now fairly mechanical. So step one is to write the likelihood function. So what is the L of theta? So it's basically I have a bunch of normal distributions. So we have product of I from 1 to n f of xi theta, and theta is a vector here. Okay. What is the individual one? So f of xi theta is really speaking, it's a normal distribution, sigma square root of 2 pi e to the minus 1/2 xi minus mu over sigma squared. So that is the individual one. So and if we have n of those, so the way we write this is 1 over sigma square root of 2 pi to the nth power. And then product of I from 1 to n, product of this ones, e to the minus 1/2 xi minus mu over sigma squared. That's step one. Step two, we compute the L theta. I believe that is our step two, right? Yeah. So L theta, the log likelihood function. So L log of L theta. So we have to take the log of this one. So let's see. So we have 1 over sigma to the square root of 2 pi. So square root of 2 pi means 2 pi to the 1/2. So this is really sigma to the n and 2 pi to the n over 2. So if I take the log function, and which since in the denominator, it's minus n log sigma minus n over 2 log 2 pi. This takes care of the first two terms. And minus, now these are products, so it will be addition. So, and since the log is with respect to e, so then all these terms will be 1/2 summation I from 1 to n xi minus mu over sigma squared. Okay, that's it. So that is my log likelihood function. Step three, we'll maximize it. To maximize L theta, we differentiate this with respect to the parameter. So now please note that it's a vector. So this theta is a vector. It has two components. It's mu and sigma. So what we have is we first have to differentiate this with respect to mu. And then I have to compute the derivative with respect to sigma. Okay. It's a fairly, it's fairly simple in the sense that, so when you differentiate this with respect to mu, the only term it will see is the last term. And when differentiate with respect to sigma, it will see the first term and the last term because both has sigma. I'll leave it as an exercise how to do it. So when it's differentiated with respect to mu, so only this term is differentiated. So it's going to be minus I from 1 to n. So minus, and then this is 2 xi minus mu over sigma. And then if I differentiate mu, it is again minus 1 over sigma. Okay. So this cancels. And when I differentiate with respect to sigma, the first term is giving me log of sigma would be 1 over sigma. So it's minus n over sigma. And then when I differentiate with respect to this one, it's minus 1/2 I from 1 to n, again 2 times xi minus mu over sigma, and then differentiate this 1 over sigma. So it's going to be minus 1 over sigma squared, right? Okay, so this 2 is also cancelled. What we do now is we set that equal to 0. So now if dl d mu equals to 0 would give me essentially I from 1 to n xi minus mu over sigma equals 0. The first term is equals to 0 would give me this one. Let's see what it gives me. So that means we have summation I from 1 to n xi minus mu is 0 if I multiply by sigma. So this will give me summation I from 1 to n xi minus, when I open the parenthesis, there are n of this mu, so it's n mu is 0. So that means I get mu equals 1 over n summation I from 1 to n xi. So that is my first estimated values. Remember, so for theta, it has 2 parts. So theta has, it has 2 parts. So it has mu and sigma squared. So I found mu. And also the other one, so L theta over d sigma equals to 0 would give me minus n over sigma plus 1 over sigma cubed I from 1 to n xi minus mu squared is 0. Let's see, this really gives me 1 over sigma cubed I from 1 to n xi minus mu squared is n over sigma. So that means sigma, so if I move the sigma here, so sigma squared is 1 over n I from 1 to n xi minus mu squared. That is my sigma squared. Okay. All right. So now, for the interest of time, I'll not show that this the second condition is also satisfied. So maybe so I'll be probably assigning this as a homework problem, but it can be shown that this mu sigma square, this mu and sigma maximizes L theta. What I mean by that is note that whenever you have these two equations and you find some mu or sigma, so that really means it's a little confusing. So this theta really means mu and sigma. Sorry, sigma. This is really mu and sigma, and that's why this we have these two equations. Now, what really it means is it's a critical point, meaning that it can either maximize or minimize, right? So what we are saying is that this, yes, these values are actually maximizing. All right, so maximizes L theta. So what is this now? We are done. So this mu and sigma squared are the thing, but remember what we did last time. So now let's try to see this as a statistic. Okay, so in terms of statistic, the maximum likelihood estimators can now be written as mu hat. So whenever I'm going for from mu to mu hat, so I'm writing this maximum in terms of statistic. So I'll write this as 1 over n. All those little xi's are now converted to big xi's, and I write this. And what is that? That is nothing but the sample mean. We have already seen this. What about sigma hat squared? So that is, once again, we have the expression here. I'll replace this little xi's by big xi's. And mu, which is the, we already found this mu value right now. Its estimator is x bar. So this is going to be 1 over n summation I from 1 to n xi. Little xi is replaced by big xi, and mu is replaced by its observed value, x bar. Right? These two are likelihood estimators. The question is which one is unbiased and which one is biased. Now this can be answered through our knowledge of the previous section, note that what is E of mu hat? It's really then E of x bar. And what is the expected, what is the sample mean, the expectation of the sample mean? That is the population mean. And what is the population mean? So here, each of these samples are drawn from a normal distribution with mean mu, variance sigma square. So this got to be mu. Hence, E of mu hat is mu. So that mu hat is an unbiased estimator of mu. Okay. However, in but what about E of sigma hat squared? It is really E of 1 over n, I from 1 to n, xi minus x bar squared. If you recall our discussion from the last class, this is not really the sample variance. Remember what we did, something really surprising for the sample variance. We didn't have n here. We had n minus 1 here. And sample variance was an unbiased estimator of the population variance. So that means we know that if we can somehow replace this by n minus 1, then whatever we have here, we know that this is E of this one is sigma squared. We proved it last time. But then look at that. We have n minus 1, so we have to compensate that. So we have to write n minus 1 over n. Right? So this is now n minus 1 over n, and this quantity, we know that this is sigma squared. That's a population. This is an unbiased estimator of the population variance, which is sigma squared. In other words, sigma hat squared is not an unbiased estimator of sigma squared. So while we estimate a normal distribution, the parameters of normal distribution, which are mu and sigma squared, we observe that whatever we find as the estimator for mu, that is an unbiased estimator, but the estimator for sigma squared is not. So that's something completely different. I mean, that's different. So that is this number. Okay. All right. So this is what we understand. Let's now solve an exercise problem so that we can feel better about with the numbers. All right, so here's an exercise problem. So this is exercise 4.1.1 from the textbook. And I'll show you the exercise. I'll not show you the, I don't want to copy and write it again because we don't have much time. So here is the exercise problem. It goes like this. So 20 motors were put on test under high temperature setting. The lifetimes in hours of the motors under these conditions are given below. So these are the lifetimes of the motors. Okay. Also, this data, again, we don't need it. So we'll not do anything with the numerical computation. So we'll simply, we'll do something with the numerical computation, but we'll not do anything with the coding here. So suppose we assume that the lifetime of the motor under the conditions X has a gamma 1 theta. Again, don't worry about this. So this is simply means that it follows the exponential distribution. So it's really exponential theta. Okay. So so we are assuming that I think according to this notation, just a second. So I believe that so in their case, the gamma distribution and exponential distribution has a slight difference. Yeah, so it's really not exponential theta, it's exponential 1 over theta. For those who took this course with me before, so and also if you're this is a standard parameter, so if gamma of 1 theta is same as exponential of 1 over theta. Okay. All right, so this particular distribution of numbers are known to follow some exponential 1 over theta. Now, we'll be skipping the first two parts. So what we'll be doing is the third part, which is right here. It goes like this. So it's obtain this. Sorry. No, we're actually doing this one. Assume that a gamma 1 theta, which is the exponential of 1 over theta model, obtain the maximum likelihood estimator of theta hat of theta and locate it on your histogram. So we'll see what it means. And next, we'll do something with that. Okay, so this is the problem. Actually, we'll not solve the entire problem, so I'll just skip it through the main results and I'll write the relevant results only. Okay. Part B. We want to find a max likelihood estimator theta hat of theta. Okay. Now, what is that? We have done it before. So what is the likelihood function? Likelihood function is L theta that is our example one right here. That's a first example. So L theta is this one. I'll simply copy it, right? So L theta done before is 1 over theta to the n e to the product of I from 1 to n e to the minus xi over theta. Okay. Hence, step 2, the log likelihood function is this one. I'll simply write the last step. It's going to be minus n log of theta minus 1 over theta I from 1 to n xi. So theta, well, to maximize the L theta, we find of L theta is done by d of L theta over d theta is equal to 0. And that gives me, we have done this computation before, so I'm doing it here pretty fast. 1 over ni from 1 to n little xi. Okay? That maximizes the thing. So the maximum likelihood estimators, there's an estimator, theta hat. How do you construct it? We check this number, so we change all the small x to big x's. So it becomes 1 over n, I from 1 to n, xi, which is nothing but the sample mean. Okay? That is actually the content of the first part of the part B of the problem. So they're asked to find the maximum likelihood estimator. Next, the question is, what is the maximum likelihood estimator in the context of this present problem? So what is the estimator in the so for the case of the present problem, for the given sample, And what's, let me show you the sample again. So the samples are right here. How do I compute the X bar? Well, how many data are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 20 data, right? I'll simply add these numbers and divide by 20. Whatever I get, that is my average, sample mean, right? For the given sample, X bar is 1 plus 4 plus da 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 up to 363 over 20. Okay. And this number, if you can compute, I have this number computed, so it's 101.15. So what's the conclusion? The conclusion is, if this data set, if somebody provides you with this data and say that, okay, so it follows the exponential 1 over theta distribution, then what is that theta? And your answer would be, okay, so if that is the case, my theta would be 101.15. That's the answer. All right, so I want to solve one more problem. So this problem is exercise 4.1.2 from the textbook. But before doing this problem, I mean, this problem is an aside. So here is a aside. It's a big aside for this one. I mean, I should have not written this before. It's the estimation for the binomial distribution. So it goes like this. So let X be 1 or 0. Okay. So it's based on the, so basically X follows the Bernoulli distribution. So probability of success is theta. Probability of failure is, remember, so X equals to 1 with probability, say, theta, and 0 with probability 1 minus theta. So in this case, we call this X to be the Bernoulli distribution. Theta. Right. Now, its probability mass function can be written in a very nice way. I mean, it is of course a probability mass function. We can write this as this way, and also we can write this as the following. We can write P of X theta equals to theta to the X 1 minus theta to the 1 minus X for X equals to 0 or 1. This is another way of writing the probability mass function. See, what happens is if I choose theta X equals to, suppose your X is 1, then it's basically theta, right? This term drops. And if X equals to 0, it's basically 1 minus theta. So it agrees completely with this. Okay. Now, if X1, X2, Xn is a random sample on X, what's the idea? I know that exactly how many number of trials are done, but I don't know what this theta is. I'm trying to estimate that. Basically, I'm talking about so this is a binomial distribution with n known, because there are n number of samples, but p equals to theta unknown. P is the theta. Okay, so the quantity theta is unknown, but the quantity p is known. Sorry, quantity n is known. So can I estimate it? So it's binomial, but not both of the terms are unknown. So k is known because I know how many samples I drew, but I don't know what the probability of success is. So step 1 is to write the likelihood function, and we know how to do it. So likelihood function, it's basically, so I'm thinking this trial of n binomial distributions. Okay, so each trial is a binomial, and collectively it'll be each trial is a Bernoulli, and collectively it'll be a binomial. Okay, I'm thinking that way. So it's basically I from 1 to n, p of xi theta. So this is same as we have written the quantities right here. We have written the quantities p's here. So let's write it down. So it's I from 1 to n. So it's basically theta to the xi, 1 minus theta to the 1 minus xi. So that's L of theta. Okay. Step 2, we compute the log likelihood function. We take the logarithm of that. So it's going to be, it's a log of L theta, which is the first term would be, it's a summation I from 1 to n xi log theta plus when I take the logarithm of this one, it's going to be, and then we take the summation. So it's summation I from 1 to n 1 minus xi log of 1 minus theta, right? Which is same as log of, summation of I from 1 to n xi log of theta, the first term. And then when I take the summation of 1, it's n. So it's I from 1 to n. When I take the summation of this one, 1, it's n. And when I take the summation of xi, it's xi. And log is just independent of I, so it just is there. So if I simplify it, it's this one, right? Step 3. Where we compute the partials and I equate that as so let's compute the partials. So the partials will be summation xi I from 1 to n over theta minus n minus summation I from 1 to n xi over 1 minus theta. If I set that to 0 and if I solve for theta, then I'll get, let's see, what do we get? So we have I from 1 to n xi over theta equals n minus summation I from 1 to n xi over 1 minus theta. So summation I from 1 to n xi, I'm multiplying with this one, minus theta I from 1 to n xi equals n theta minus theta I from 1 to n xi. These two terms cancel. So my theta becomes 1 over n I from 1 to n xi. Okay. Which is, so the maximum likelihood estimator theta hat is 1 over n. I'll convert this little x's to big x's. So it's xi, and this is our old friend sample mean. Okay. So for the case of the binomial distribution, so for x which is satisfying binomial n theta, where n is known and this is unknown, an estimator, the maximum likelihood estimator, is the proportion for theta, is the proportion of success in the n trials. Please note this very carefully. It's a very important result. What do you mean? It's a sample mean, that's right. But what is a sample mean? So xi's, so remember that the xi's equals to 1 if success, and it's 0 if failure. So this quantity is summation of xi. It counts the number of successes, right? So it's, what is theta hat? Theta hat is the number of successes over the total number of trials. So the estimator for this theta is the proportion of success out of n trials. So that's always the case. So for a binomial distribution, so if I want to estimate this theta, so or the probability of success p, that's always the if I look for an observation and so whatever proportion of success are there, and it's so that is giving me the exact number. Okay. All right. Now again, I was trying to this is an aside result, but what I was really trying to do is this exercise problem. So let's do it now. So this is the exercise problem number so exercise 4.1.2 textbook. Okay. What is this asking is the following. So here are the weights of 26 professional baseball pitchers. Okay. And these are the weights. Okay. I'm focusing on part C of the problem. Using a binomial model, obtain the maximum likelihood estimate of proportion P of professional baseball pitchers who weigh over 215 pounds. So let's just focus on part C. Okay. So we want to estimate probability of X bigger than 215 using a binomial model. Now it got to be very easy. Why? Because we have just seen a result. So how do you estimate the probability of this kind? So basically, the proportion in the sample is an estimator for the proportion in the population. So this quantity is really estimated as PB hat is the number of baseball pitchers who weigh more than 215 pounds over the number of total population, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 26. So out of 26 players, so let's see how many weigh more than, so X is my weight. So X is the weight. So 215, so that means all this less than 215. So it's 1, 2, 3, 4, 5, 6, 7. So there are 7 players who weigh more than 215. So it's 7 over 26, which is 0.2692. Okay. We know that we have just seen this particular result. It goes, I mean, this one, that the maximum likelihood estimator is the proportion of success in n trials. In our case, n is 26, and success means weigh more than 215 pounds. Okay. So in our case, the sample result is 0.2692, and hence the required proportion answer. That means for the population, for the entire population, based on it's a tremendous claim. Like based on these 26 players, we are saying that for all professional baseball pitchers, what is the proportion that is that weigh more than 215 pounds? We're saying that required answer is also 0.2692. That's it. Okay. That is based on the maximum likelihood estimator. Okay. One last problem and we are done. Let's do number 16. Sorry, the next problem, which is exercise 4.1.3. It goes like this. Suppose the number of customers X that enter a store between the hours 9 a.m. and 10 a.m. follow a Poisson distribution with parameter theta. Suppose a random sample of the number of customers that entered the store between 9 a.m. and 10 a.m. for 10 days result in the value. So we have this bunch of values. Okay. Determine the maximum likelihood estimate theta and show that it's an unbiased estimator. Okay, so that's the first part we'll show. And second one, based on the data, obtain the realization of your estimator in part A. Explain the meaning of this estimate in terms of number of customers. So there are two parts. The first part has nothing to do with this data. First part is theoretical, and second part will be using this particular data. Okay, so let's get started. So what we have is the following. So we have a Poisson distribution, and we have the data for the Poisson distribution. So we can write this as let me remind you. So Poisson distribution, where the probability of k is probability x equals k is given by e to the minus lambda, lambda to the k over k factorial, where k equals to 0, 1, 2, so on. That's something we'll know. Okay. Here the unknown is lambda. Okay. So we know this form. So this in our case will be written as p of k theta, or more so our notation will be p of x theta. So new notation. All this is the same thing. So p of k is same as p of k theta, just to emphasize the dependence of lambda, and lambda is theta. And I'm just writing this as p of x comma theta. Okay, just replace the k. So my x values can be 0, 1, 2, so on. Okay, step 1, part A, where we have to find the maximum likelihood estimator of this this quantity. So here L of theta is really I from 1 to n p of xi theta, which is really I from 1 to n e to the minus theta, theta to the xi over xi factorial. So there are n of this e to the minus I there, so it's e to the minus n theta. Then I can write this as product of I from 1 to n, theta to the xi over xi factorial. Okay. Step 2, take the logarithm of that. So log likelihood function is log of L theta, which is minus n theta plus summation I from 1 to n xi log of theta. And then this term, it's minus I from 1 to n log of xi factorial, okay, whatever that is. Step 3, to maximize this, so we have to compute. So it's a function of one variable, right? So I can simply write L prime theta equals to 0 would give me, so let's differentiate everything with respect to theta. So this is my L theta. And I'll differentiate this with respect to theta. Note that last term does not have in theta, so it goes away. The first term has theta, so it's minus n. And then log theta, if it differentiates 1 over theta, so it's 1 over theta I from 1 to n xi equals to 0. So that means my theta is 1 over n I from 1 to n xi. First observation. And now this can be a max or mean. So let's compute the second derivative. So also L double prime of theta is what? So if L theta equals to this one, L double prime would be, so minus n is going to 0. So it's minus 1 over theta squared I from 1 to n xi. And my samples are drawn from Poisson distribution. So everything is positive here. Theta is also positive. So this number is negative. So hence, we really maximize, because remember that L prime theta is 0, L double prime theta is less than 0. That means that this theta, whatever this value is, it's actually maximizing. It's from calculus. If the second one is positive, that means it's minimizing, but we really want the maximizer. So here it's fine. Okay. So the first answer, what do you claim here? So we claim that what do you have to find? Let's see. So here, the first part is asking that determine the maximum likelihood estimate of theta. Remember that the MLE of theta, it's an estimate. So I have to write this in terms of statistic. So statistic is in terms of I have to write this little x's with the big X. So it's 1 over n, I from 1 to n, xi. But suddenly when you write this, you realize that this is nothing but x bar. It's a sample mean. So the maximum likelihood estimator of theta is x bar, the sample mean. Good. The second part it says is show that it's an unbiased estimator. Well, we know what. So E of theta hat, which is really E of x bar, it's a sample mean, which is equal to the population mean, which is same as the E of x1, E of x2, etc. This is what I mean by population mean. Everything are following the same distribution. What distribution? They are following a distribution of the Poisson distribution with parameter theta, right? So I assume that everything, I mean, the unknown is lambda. So this everything is following a Poisson distribution with parameter theta. So that's what we assumed. So that means what we assumed is E of x1 equals E of x2. All this E of xn is theta. Remember that the parameter value is same as the mean of the Poisson process. A Poisson, sorry, not process, Poisson random variable. So that means this is equal to theta. So what we found is E of theta hat equals to theta, and hence that the maximum likelihood estimator of theta is an unbiased estimator. Okay. Done. First part done. Part B, where we use the data, it says that based on this data, obtain the realization of your estimator in part A. Which data? The data which is provided. So based on the data, what is X bar? So it's basically it's very few data. So we can compute 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's basically 9 plus 7 plus 9 plus 15 plus 10 plus 13 plus 10, sorry, 13 plus 11 plus 7 plus 2 plus 12 over, say, 10. Okay. If you compute this, this is 9.5. Okay. So this is, so based on data, so we answered the based on this data, obtain the realization of your estimator in part A. So this is my theta hat. Okay. Finally, explain the meaning of this estimate in terms of number of customers. So let's, so what does it mean? So this is the, I mean, everything here is telling us something about a statistical quantity. Now, the question is what kind of quantity we are defining by this one. So if you recall, what does the number theta say? It says the average number of customers per day, right? So what we found here is 9.5. So that means that the estimated 9 number of customers that enters the store between 9 a.m. and 10 a.m. is 9.5 based on the data. So approximately 10 customers, this 9, there cannot be 9.5 customers. So it's approximately 10 customers are entering the store between 9 a.m. and 10 a.m. On a given day. Okay. All right. So this is how this is all about the maximum likelihood estimator. I understand this section is a little bit difficult. So please revise the book and study this section. If you have any question, feel free to send me email. I'll be happy to meet you with you, and we can discuss any question you might have. Okay, thank you very much. I'll stop the recording.